Okay, so good afternoon to all of you. So let us just revise some of the uh, definitions which we discussed in recent days. So in previous lectures. So this is a product topology. Product topology is a topology generated by the bases whose elements are of the form U cross V, where U is a element of topology on X and V is a element of topology on Y. So this basis generates the topology which we call product topology, and we also know that the product topology is also generated by another basis, that is, so basically this is product topology which is union of all basis elements, and we have also seen that it has another basis which I gave as an exercise, that if I take all the sets of the form B cross C where B is basis of X and C is a basis of the topological space Y, then all such sets forms a basis on X cross Y, and it generates a topology. That topology is same as the product topology. So basis we already checked, but the second part was given as an exercise, and the exercise can be done using either this result, and in particular using a small result that says that if one basis is contained in the topology generated by another basis, then the topology generated by first basis is subset of the topology generated by second basis. So whenever I want to show one topology generated by one basis is contained in topology generated by another basis, we can use this result. So only thing I have to show is this. So that is meaning of this result. And one example of this we have discussed is the two topologies on R cross R. One is generated by open disk, another is generated by rectangular regions. Then we discuss projections maps. So on X cross Y we can discuss two projections. One is over projection over X, another is projection over Y. So pi 1 is projection on X, pi 2 is projection on second coordinate Y. And so it is like orthogonal projection on x-axis and y-axis, and these maps are known as projection. And then we have discussed the inverse images of these sets. So they are the open horizontal strip and vertical strip. So in xy plane or in R2 plane, if I collect all the open vertical strips and horizontal strips, that means the strips between two lines, then the region between two lines, then this collection forms the sub-basis. So that is a small result which we discussed, and so this collection, we know that if I take vertical and horizontal strip, then I intersect, then I get U cross V basically. So this is the result. So this forms a sub-basis of X cross Y of the product topology on X cross Y, and so that is this lecture. And in the next lecture we discuss continuity, that is the previous lecture. If X and Y are two topological spaces, that means I have a topology on X, I have a topology on Y, and if I was function from X to Y, so here function from X to Y, but basically X has the topology along with X, so I can write X comma Tx to Y comma tau Y. So basically function is from X to Y. X is domain, Y is codomain, but on X we have a topological structure. Similarly, Y we have a topological structure. That means we know all the open sets in X, we know all the open sets in Y, and f is a function from X to Y. So if I have such a function, then when we say it is continuous whenever I have V is open set in Y, then I should get inverse image of V should be open in X. So that is exactly this criteria. And you must have come across this definition because it is discussed in the Rudin's book as well as other books where metric spaces are discussed. In particular, Rn also we use the same definition. Function from R2 to R2 is continuous. So that there also we come across this notion, and we in remark we observe that if I have a function from R to R, then it is continuous with respect to this definition. That means inverse image of open set is open. Then I can prove the epsilon delta definition follows from this definition. That is what we discuss here, this result. And I mentioned that converse is easy, so you can try to prove that it follows very simply, but of course it needs some argument. So you have to observe that basically. And this lemma says that if I want to check function is continuous, then by definition I should check inverse image of open set is open. Each open set is open. But this result says that now I should check only on the basis elements. So if I want to check some function is continuous, and if I use this lemma, then I need to check only that inverse image of every basis element is open in X, not on every open set, right? If I go by definition of continuity, I have to check for every open set. But then this lemma says I don't need to check for every open set. I need to check only for the basis elements. That is meaning of this lemma. So this is some basic results on continuity. Only one lemma we discuss. Later on we will come across several results. So after that we discussed so this exercise I have given because this is used in the lemma, so which you can try. It is just simple exercise in functions and basically set theory. So first you try this, then this will be easy. So you can consider this as a hint or a special case. So one more definition we discussed last time is the definition of closed set. So now we know that if I have a topology on the set X, then each element of the topology are called the open set. So then what is the closed subset of X? So a subset A of X is called closed if by definition its complement is open. So complement is open means complement should be in the topology. So whenever X minus A belongs to tau X, we will say A is a open set in X. Now we've seen some examples that closed interval AB is closed in the standard topology because its complement is open intervals, union of open intervals, and union of open interval is open. So therefore this closed interval AB is closed set in the standard topology on R. Then we discuss cofinite topology. So what are the closed sets? So X equal to N is closed because its complement is null set which is open, and on the other hand each finite set is open. Every finite set in the cofinite topology are closed sets, and complement of finite sets are open. So the question which at the end I have given is, what are the closed sets in the discrete topology and lower limit topology? So anyone tried this question? What are the closed sets in discrete topology?
Yesterday, sir, you told us that what will be the closed sets.
Yes, so yesterday I have given some idea that all the subsets of X are closed. So let us start with that example. Okay, so let X be any set, and let tau X be the discrete topology on X. So suppose A is a subset of X. It may be empty set also, doesn't matter. So if you want, you can discuss empty sets separately, otherwise that is also fine. So what can we say about A complement? So whether A complement is also subset of X?
If it is discrete topology, then yes, because
Yes. So then
all the
what is,
power sets element will be there, so complementary will be there.
yes. So but the question was that A is a subset of X, then whether X minus A is a subset of X. So that is always true, right? Because if A is a subset of X, then if I remove elements of A from X, then still it is a subset of X. So therefore A complement is subset of X, and then we know that every subset of X is open. So therefore what you said is, now we are using that A complement is in tau X. It is open with respect to discrete topology, because tau X is discrete topology. So now we know that A complement is open, that means A is closed, right? So what we proved is, I started with any arbitrary set which I proved that it is closed. So therefore what we proved is every subset of the universal set X is closed with respect to the discrete topology. And open as well. Yes, open we already discussed. So that is also true, that every subset is open as well as it is closed. So some books use such a notion as a clopen kind of thing. So clopen means closed plus open, but this is not a standard terminology, but some books or some faculty use that. Okay,
So
so we,
only this is the discrete topology where we get the group, and our other topology should be there where we get closed and open both in the same set.
yes, so that for that let me discuss first some small result. uh, regarding closed sets. So let X be a topology. So what are the possible trivial subsets which are always closed? So
Phi
let
and X, phi and X.
right. So they are the always closed as well as open. So let X be a topological space, any topological space. Then the following statements hold. So, so basically we are discussing the properties of closed set. So we know property of open sets that if I take a open sets, then arbitrary union of open set is open, finite intersection of closed of open set is open. So what about closed sets? So first property is that phi and x are always closed. So these sets are, we already know that they are open because they belongs to tau for every tau, and now we are saying they are also belongs to tau for every tau because their complements. So both are close with respect to every tau because its complement also belongs to tau. So arbitrary. So what are the properties of closed sets? Arbitrary intersection of closed set is closed. And third property is finite union of closed sets is also closed. Okay. So proof is quite trivial because since phi and x belongs to tau, so let tau be the topology on x, the given topology on x. So usually we write tau x, but now here in the statement only one topology we are discussing. So I will denote it by simply tau. So for first property, since phi and x belongs to tau, that means phi and x are open. So they are open that then complements are closed. So what we get is phi complement and x complement are closed in x or with respect to tau. So what is phi complement? That is x, and x complement is phi. So these both sets are closed subset of x, right? So phi and x are open also, phi and x are closed also. So for example, real line is a closed set also, it is open set also, and null set is always closed as well as open. Second property, we want to show that arbitrary intersection of closed sets is also closed set. So let us take family of sets be a family of closed subsets of x. So what is meaning of this? A alpha is closed, that means its complement is open, right? By the definition of closed set. So this is open for every alpha. Now we know that if I have a family of open sets, then its arbitrary union is also open set. So therefore, union alpha, A alpha complement is also open subset of X. Right. So now what can I say about this set? So this is actually X minus A alpha. So we can also write as X minus intersection A alpha. So this is open set. So what this says, the complement of this set is open. So therefore intersection A alpha is closed. Right. So basically we are using the property that arbitrary union of open set is open to prove the property that arbitrary intersection of closed sets is closed. So is it clear this proof?
Yes, sir.
So we are just simply using set theory. And the third part is also similar. So now we have to take only finite connections. So let's say I is equal to 1 to n be a finite family. Finite family means finitely many family of closed sets. So we want to show its union is closed. So to show its union is closed, we have to focus on the complement of that, and we need to show it is open. So what is the complement? Complement is intersection I running from 1 to n x minus ai, and then we know each x minus ai is open because each ai is closed, so its complement is open. So therefore what we'll get, so each of these is open, and then we know finite intersection of open set is open. So therefore this set is open, and hence we will get this set is closed. Right, so these are just simple properties corresponding to the closed sets. Whatever properties we have for the open set, we have the corresponding properties for closed sets. Okay, so now let me go back to the lower limit topology. So what is lower limit topology? Generated by the basis B. What is the basis for lower limit topology? It is close open intervals where A is less than B. Right? So question is that is the interval 1 to 2 closed in towel? So what is your opinion?
Check.
So
Neither open
basically,
nor close open.
so let us check that. So for example, if I take let I call this set A, so that is from open 1 to close 2, and then if I want to check this set is closed, then I need to check that its complement is open, right? So basically we are lower limit topology is defined on the real line. So basically here we are taking x equal to r. So what is the complement of A?
Yes, sir. It's close, I
Right?
think.
Yes, so it is close. So you have checked it. So let us verify for the other students. So A complement is we need to check that it is A is closed. So we will check. We will show A complement is open. So what is A complement? A complement means R minus interval 1 to 2, open close interval 1 to 2. So basically what is this interval? This interval uh, is from minus infinity to 1 closed union 2 to infinity. So what is the basis element? Basis elements are of this form. So can I show that this set is union of such intervals? If I can show that, then this set is open and therefore this set is closed. So now because tell me whether it is true.
Sir, I checked for close interval, close 1 comma 2
Close one. Okay.
instead of
So we can
So
take sequence, then it will converge to minus infinity and 1.
sequence. So let us go one by one. So whether this set is open or not.
It's not open, but we can make it open by 1 plus 1 by n, and in the first term 1 by n minus 1 by n, comma 1 plus 1 by n.
Yeah. So what I'm asking is, can we write this set as a union of basis elements? So
Yes,
what you
yes.
are suggesting is correct. Yeah, because on the right hand we have open intervals, so we have to take exactly the sequence idea. So exactly what we will do. So you are suggesting we can write this as a union n 1 to infinity minus infinity to. So in fact, first of all, I have to reach up to 0. So let us take union of minus n to 0 kind of thing. So this will give me open interval minus infinity to 0 is the union of this, right? And then I will need some another set. So that will be union n 1 to infinity 0 to. Now what you are suggesting?
Sir, I think, yeah, we can write minus n comma 1 plus 1 by n. or 1
What
plus 1.
about this set?
Yeah. But
Wait,
these sets are not, sir, in the basis. It
right.
should be.
So actually I did mistake. So it should be closed on the left side.
Yeah.
So what about this? Is it correct now?
So it's better, sir. We can combine both of them and write minus n comma 1 minus 1 by n.
Okay, so that is also good idea. So directly we can combine this, merge these two. So 1 minus 1 by n. Right. So this is more simpler. So now just check whether this covers all these points. No, but you are saying one will be left, right? So therefore you are saying we have to take plus kind of thing.
If we take plus, then again.
What if we do for example I am taking it up to 0 and how to add 1 is not clear to me. So if I have a collection of open intervals, can I make how to get a union to be 0? So what is this union?
It will be
It
by
doesn't.
x. Yes, because one another side it will be 1 and
Yes. So what about one? So one on the left side we can do what? Right side it is not clear. So this is a difficult question for me actually now.
no, it's I think using complement. Can,
So I'm asking that whether this set is closed in the lower limit topology. So it is clear that all the sets of the form minus infinity to b are open in towel because I can write it in this form. But what about this type of element and this type of element? So this element, it may happen that it is not closed, right? It can also happen that. Let us postpone this question. Maybe it will take some time. So before, so you try it as an exercise. I will also see whether it is easy or not. Whether because sequence approach is also not working. So we can check it as an exercise now. So similar example, let me discuss for the subspace topology.
सर क्लोज वन ओपन टू ये तो क्लोज हो जाएगा.
Closed interval 1 to 2.
टू की तरफ ओपन, वन की तरफ क्लोज.
क्योंकि इसका
यस, ये क्लोज हो
left
जाएगा.
side closed you are saying or closed open you are saying?
क्लोज ओपन और टू की साइड ओपन. हाँ
Open.
ये.
So
हाँ ये
then this
क्लोज.
will be what? This will be minus infinity to 1 union 2 to infinity.
बोथ आर ओपन सेट.
So yes, so this is also open set, and this cell also we can write as a union of basis elements. So therefore this is open, and therefore close interval 1 to 2 is closed.
सर लोअर लिमिट टोपोलॉजी में -1 to infinity ओपन है, मतलब दोनों साइड तो क्लोज,
What -1 to
-∞ to 1
closed one or open one?
ओपन।
ये तो वैसे
हाँ, तो इसका क्या है, ये ओपन क्यों है, ये पूछ रहे हो?
हाँ,
Because it is union of these elements.
कैन बी रिटन एच स्लो।
Yes.
अच्छा अच्छा,
So you just take minus n to 1, right? So that will be the same set, and all these are basis elements.
बेसिस एलिमेंट का तो एक साइड सर ओपन है और एक साइड क्लोज है, इसमें तो दोनों ओपन ही दिख रहा है।
Yes, so you are right. So this is left side should be closed. So now it is okay.
हाँ, यस सर।
So this set is also open, and similarly we can show this is also open. We can take close interval 2 to n, and we can take union of that. Alright, so this is closed. This set is closed. I think here we have taken open interval, right? Closed 1, open 2 is closed. So close, so this set is also closed, that means. And what about this type of sets? So that is not clear whether it is closed or no, or open. So that you can check as an exercise. This type of set, whether it is closed or open, or whether it has limit points or not. So that we may postpone this discussion after discussing the limit points, because it is not clear whether this set is closed or open. So you can try this as an exercise. So is open interval 1 to 2 closed set with respect to lower limit topology? So that is what we discuss, right? Okay, so this we discuss. So next I want to take is a subspace topology. So let me just discuss another example. So is the set close interval 0 1 union open interval 2 3. So whether this is closed set with respect to subspace topology, so is close interval 0 1 is closed in the subspace topology with respect to y. So subspace topology means can anyone recall what is the definition of subspace topology?
By is equal to b intersection y.
That is a basis. And what are the open sets? So they are of this form: u intersection y, where u is element of tau x. So whenever y is a subset of x, so here y we are taking subset of a real line. So what is the set? Set is closed 0 to closed 1 union open interval 2 to 3. So this we are taking the union of these sets, that is y. So what is tau y? Tau y is basically u intersection this set close interval 0 1 union open interval 2 3, where u belongs to u is open in R. So
Our
first
axis
question,
R.
pardon,
Axis R.
x is R, yes, that I mentioned here. So x is equal to R. So we are taking subspace topology. Subspace topology means I have a set which is a subset of some other set. Whenever I have y which is subset of x, and on x I have topology x, then I can define topology on y using this tau x. So that is subspace topology defined this way. So all the open sets in the subspace topology are of this form. Some open set in R, its intersection is y. So first question is close interval 0 1 open in tau y, that means it is element of tau y.
Yes, a subset of y.
It is a subset of y, right? But
It's
whether it is open or not, that means whether it is of this form or not. So in other words, is close interval 0 1 equals to u intersection y for some open subset u of R. So can I find an open set u on the real line so that u intersection this set is exactly close interval 0 to 1.
yes sir, u to मिल जाएगा u 0 to 1 लेने से, तो इंटरसेक्शन में 0 to 1 आ जाएगा each element.
So mainly if I take the simple open set, so they are the basis elements. So on the real line we know basis elements are intervals. So can I find some open interval a to b such that if I intersect that open interval a to b with y, then I get only this set. So what is the possible value of a and b?
-1 to 1.5.
Right, so such a value I can take. So because I need close interval 0 1 inside. So that means I have to go left side of 0 and here you can take any value between 1 and 2. So for example 1.5. So uh, this is true because close interval 0 1 is intersection of -1 or -2, you can take whatever you can take, and then its intersection with y. So this union 2 comma 3, right? And then so therefore this is open in the subspace topology. Topology tau y. So is it clear close interval 0 1 is not open in real life?
फिर से एक बार बताइए सर,
Yes.
फिर से एक बार एक्सप्लेन कीजिए सर। ऊपर में सर एक जगह इंटरसेक्शन यूनियन, वहाँ पे मैं थोड़ा गड़बड़ हो गया समझने में। यहाँ पे
ये
सर
union,
यूनियन होगा
this is not union, this is u.
नहीं, इसके बाद वाला सर।
इसके बाद ये तो
नहीं
y
नहीं,
है,
उस
this is basically y.
यू के ऊपर ही सर आप जो लिखे हैं 1,0,
This one.
उसका उसका नीचे सर, पर वही मैं कंफ्यूज हुआ था। नीचे सर, इसका एक स्टेप नीचे, ये वाला
ये
लिखा हुआ है। हाँ,
हाँ.
इसमें
So
सर,
if
इसमें जो
I so basically I am taking u to be the open interval AB
और इसके
because
बाद
that is open subset of R.
इंटरसेक्शन
So,
फिर 0 0 1 इंटरसेक्शन 2 3।
no, that is union. So you are right. This is just typo. So I think next if I have written correctly. So here this is wrong actually. So that was typo. So now you are correct that this is our y.
यहीं से गड़बड़ हो गया था सर, कंफ्यूजन हो
Hmm.
गया। फिर से एक्सप्लेन करते हैं।
So if I take the close interval 0 1, I want to check whether close interval 0 1 is open with respect to subspace topology on y. So if I want to show that any set is open in the subspace topology, then it should be of this form, where u is open in the x equal to r here. So what choice of u I will take? So u is a subset, open subset of R. So in particular, I can try for the basic open set. So basic open sets are open intervals with respect to standard topology. So can I find a basic open interval close interval A to B such that intersection of close interval AB with Y, that is this set, is given set? If I can do that, then this set is open. So what are the possible value of A and B? So that what you suggested is correct, that we can take the interval -1 to 1.5. So if I take this as U, then clearly U is open in R, and U intersection Y is this set. So therefore this is open
यस सर, अंडरस्टूड।
in the subspace topology.
ओके सर।
Now this set is open in subspace topology, but this set is as a subset of R is not open in the standard topology. So is it clear that this set is not
यस
open as a
यस सर।
subset of R, because we know in real analysis this set is closed. Close interval 0 1 is closed, right? So it is open in the subspace topology. However, close interval 0 1 is closed in the standard topology on R. what can we say about open interval 2 3? So is 2 3 open in the with respect to this topology, subspace topology on Y?
इस टाइम नेक्स्ट वाला ले लेंगे सर, नेक्स्ट वाले का
So
हेल्प लेंगे.
what we need to show, we need to find open set U of R such that open interval 2 3 is U intersection Y. So here what will take U to be? So
Sir, can we please stop here because we have quiz now.
okay, you have quiz. So okay, so you just take this as an exercise. So let me stop the lecture now.